So welcome everybody. My name is Regan Murray and I'm from the U.S. Environmental Protection Agency, and I'm really glad to be able to welcome you to this meeting today on behalf of our EWRI Task Committee on Premise Plumbing Modeling. We were so disappointed to have to cancel the in-person workshop that would have been happening today, but we're very glad that you could join us here today by video for this overview session that will highlight the key research areas that are needed to advance the premise plumbing modeling. So we definitely hope that you and your families are doing well and staying safe during the global outbreak, and we're just glad that you could all be here today by video, so thank you. Before we start, I just wanted to say a few words about the importance of premise plumbing modeling to the U.S. Environmental Protection Agency. About 15 years ago or more, we started thinking about premise plumbing modeling as we were assessing the risks of intentional malevolent contamination of drinking water within large buildings in urban areas. And several of you on this meeting today were involved in some preliminary modeling studies at that time on that topic. Modeling in that case was used to help assess the risks of those types of terrorist attacks. Later, in about 2014, as I recall, after the Elk River chemical spill in West Virginia, our interest in premise plumbing modeling was renewed. In that case, contaminant had gotten into many homes in a large community, and people were evaluating how best to flush the contaminants from the premise plumbing and all of the water-using appliances in homes. And in that case, premise plumbing modeling would have been very useful to help design effective flushing programs for different types of homes and buildings, and also different types of contaminants. Our research in that area our interest in that area has grown again very recently with the coronavirus outbreak, where we're also looking at cases where there are, in this case it's different in that a lot of homes and businesses may not be occupied at the moment, or the water is not being used in businesses that are shut down. And there are questions about how to maintain water quality in those businesses, and in particular, how to maintain water quality once the businesses are reopened. And so again, good flushing protocols that could be designed based on good models are needed. EPA also is interested in modeling particular contaminants that can occur in premise plumbing systems like Legionella and lead. So we've partnered with other federal agencies in the U.S. To help buildings like hospitals and other large buildings that are concerned about Legionella risks. And many of those building owners are looking at disinfecting or treating the water within their building to reduce that risk. And it's been recognized that premise plumbing modeling would be very useful to help design effective treatment systems for those large, complex buildings. With the lead and copper rule, where we know we have the sources of lead within premise plumbing, from the lead service lines to other components within homes, there have been a lot of questions about how you can assess the risk to customers living in those homes. How likely are they to be exposed to lead, and at what concentrations? And again, that's an area that premise plumbing modeling can definitely be used to help answer those questions. We've started doing some experimental work within our research offices at EPA, both developing experimental home plumbing systems that replicate real plumbing in homes, and also validating different chemical reaction models, and beginning to build a modeling framework to address that issue. And then finally, just wanted to mention we've also been concerned about other premise plumbing issues related to natural disasters. In particular, we worked with the state of California over the last few years that had a lot of wildfires in which plastic pipes within homes were actually melted, and that caused a variety of different contaminants to enter homes. So we've been looking at chemistry models for the adsorption and then the eventual desorption of those contaminants back into the home, to really understand how long you might need to flush the premise plumbing, and how long there might continue to be contaminants desorbing from those pipes and causing health risks. So as you can see, there's a great number of important public health concerns that are associated with premise plumbing, and the development of high quality validated premise plumbing models will go a long way to help us address those issues. So many of you on the video today are aware of lots of other applications that might require premise plumbing modeling, and all of you are here because you bring significant expertise to bear on this challenge that we have in front of us. You represent the many stakeholders in this research, coming from a variety of groups, from government, private sector, academia, the drinking water sector, plumbing standards, and building management. And we're so glad to have such a wide range of stakeholders represented in this meeting today. So I want to thank you for participating. And before we get started, I'll just share a few of the logistics for the meeting. So as Tara mentioned, she is recording this, and that is so that people who are not able to attend today will be able to look at this later and listen in. We ask you to please mute your audio unless you're speaking so that we don't hear background noise, and I appreciate everyone doing that. We won't have any video on except for those of the speakers, so if you could turn your own video off unless you're speaking, that would be great. That's just to lower the bandwidth and make sure we don't have any issues with this meeting today. Let's see, in case anyone is having trouble, there is a separate phone line you can call into, and we did send out the PDF of the presentations, and in case you're having any trouble with the video call, you can just get off and call in and look at those slides from the PDF file. So I think that's it for logistics, and again, we're very glad you're here today, and we're looking forward to going through this agenda with you today, and then at the very end of the call, we'll talk about the next steps, how we're going to continue the momentum with addressing all of these important issues as we go forward. So thank you very much, and I'll turn it over to Junasuk.
Thank you, Regan. So, okay, so let me first go over the EWRI, Environmental and the Water Resources Institute. I believe most of you are very comfortable already know the EWRI. And then EWRI, very briefly, it's ASCE's technical arm for environmental and the water-related issues. And then currently there are about 25,000 members within EWRI. And PPM, Premise Plumbing Modeling, which was established last year, November, and then it's a task committee of the WDSA, or Water Distribution System Analysis Committee, and then it has a lead in EWRI in advancing the area of premise plumbing modeling. So the purpose of today's webinar, and originally supposed to happen as a face-to-face workshop, but the original purpose is to advance the science of the new field of PPM, premise plumbing modeling, and then help developing building water systems management tool for use by practicing engineers, as well as larger WDSA or water distribution systems research community to support the safe design and operation of water distribution systems. So having said that, I will turn over to John, our moderator today.
Thanks, Junasuk. We're actually ahead of schedule, so I will act as the moderator. My name is John Burkhardt. I'm also with the EPA. And for each of the sessions, there's just going to be a little intro to orient everybody, but I think everybody on the call probably is well versed in all these topics already. I guess because we have a fairly good turnout, I'm just going to go ahead and start, just because maybe we'll give everybody a little bit more chance to get questions at the end. So the first session's going to be about the premise plumbing modeling area. And so the major theme of this task committee and this workshop is to engage with the modeling experts within the Water Distribution Systems Analysis Group, EWRI, and elsewhere to support premise plumbing issues. As Regan discussed, this topic area is meant to capture the needs, challenges, and unique features of premise plumbing systems pertaining to modeling, specifically their smaller pipe size, complex layouts, and usage patterns. Tools designed for premise plumbing modeling may be like those for their larger cousins for distribution networks, but may also require unique features that can address the challenges of modeling premise plumbing not found in other pipe networks. The EPA has been working on developing, leveraging, and expanding these tools to better understand and model premise plumbing issues, namely water quality as it pertains to exposure and mitigation efforts like flushing. The first speaker is Tom Walsky from Bentley Systems, and he will now present an overview of premise plumbing modeling topics.
Okay, thank you, Jonathan. Everyone hear me all right? Someone want to indicate? Okay.
Yes.
Okay, great. I'm going to be talking about what you can do right now out of the box with our existing models. They're generally 2D models, which is a problem when we're working with 3D structures. But there's some tricks and things that you can do, and just did some experimental work with a trivial model just to show how things can work. So this can be with WaterGems or EPANET or any of those softwares. If you want to do building premise plumbing modeling right now, this is how you do it. Next. Okay, so a couple of topics we're talking about. The fact that we are working with 2D models in general in a 3D world. We can track both water quality, though, in hydraulics in the building. The solvers don't care if you're in a building or underground or exposed piping. They don't really matter. The big problems are going to be bringing in good elevation data automatically. With system modeling, you have usually a digital elevation model that you can use to build your models very quickly. You don't really have that sort of thing in a building, although you do in other ways. One of the other things we'll talk about is the fact that water use in buildings now gets down to pulses. It's no longer these nice smooth demand patterns. And then we'll talk about how to look at the results. Next. Okay, here's my trivial model of a system over on the, let's see, do you see my pointer when I'm moving it, or is my pointer not visible? No, I guess it is somebody else's hand I see is moving around. Okay, this is what we have to do when you're trying to do a building in it with the standard kind of 2D models is break the floors up into individual models. So here is the building that I built. It's a 3-story building. There's this. We're going to treat the main in the street as a constant head source. Now, this isn't always true, but usually most buildings don't have a significant impact on the distribution pressure. So treating this as a constant is not too bad, or giving it some kind of pattern. And then we just laid out each floor with its own little plumbing, and we'll go over what those floors look like. Next. Okay, so here's what they look like. I had some builds here. I was going to show each one individually. So each floor is going to have its bathroom there with the sink and the ladies' room and the toilet and the men's room. And over on the other side of the building is going to be a kitchen sink. So this is what our trivial building. Each of the floors are going to be symmetrical just to make my life easier. And next. Okay, and so you can run it. And this is run the model with those patterns. I used just a random number generator to make my demand patterns up. And I had nobody in the building at night, and then all these different uses of the water during the day. And you can just color code by these elements and see which faucets are being run now, which toilets are being flushed. And you can color code in particular. Now I'm doing it by velocity of water in the pipes. And this looks really impressive. You just let this thing run as a time simulation. You can see all these building water uses flashing on and off during the course of the day. And it's a good way to illustrate what's going on and to track the water quality. So it actually looks pretty good. You can see, okay, there's a guy that just flushed a toilet and gee, he didn't wash his hands, that sort of thing. Okay, next slide. Okay, and this is what the results look like. And for my little model, this is the results. We see that at night the pressure is flat because we're not going to have anybody in the building doing much. And during the day, you see the fluctuations in pressure. In this particular case, we can do this for any property. And the red is the bottom floor, so you get good high pressures. You got the second floor, the pressures are lower, and on the third floor we have the green things, which are lowest pressure the higher up the building you go. So we can do all these kind of things that you can do right now in any modeling, which is what I'm trying to show is that we can do building modeling with the existing tools that are out there. Next slide. Okay, so this is a water age model. So we see here that at night, the water age goes zooming up really high. And then as soon as people start using water in the day, the travel time through these buildings is not very fast, not very slow. It gets there fast. So as soon as people start washing their hands or going to the bathroom or filling up the coffee maker, the water age drops dramatically. Now that's the age versus the age of the water in the street that you're starting with. So you can also have a distribution system model that can model the inflow. But in this case, I'm just using that as a constant at 0 age. But the age isn't too bad. That first glass of water somebody takes out of the faucet is going to have some older water. But even so, unless it's a huge building, it's not too bad. Next slide. Okay, and then we can actually look at the color code by velocity and see which pipes at any time have velocities there. So we do velocities and demands, and this is useful for seeing where the water goes. So this is the age in this particular case. So you can see, at a certain hour today, some of these lines haven't been operated yet, so they're getting old water. While the ones that have been operated, it doesn't take very long for them to get flushed out with clean water. Okay, then the next part of this is rooftop tanks. Okay, the place where things really change now are in buildings that have rooftop tanks. And we're doing some work over in China where they have a lot of the tall buildings have rooftop tanks. And they really changed the dynamics, and they changed the water age pattern pretty significantly. They keep the pressure a lot more stable, but they affect the water quality because the water age in these tanks can be pretty high. And this is some work that we're doing over there that is showing that this is going to be a bigger problem than the ones that don't have tanks. So tanks, just like in water distribution systems, so you're having problems with old water, you look at the tanks because that's usually where most of the aging occurs. Okay, next. Well, what you should be seeing right now is just modeling the flow and the depth in the tank. And you see that the tank levels will fluctuate during the day, and then at night, the water age in the tank creeps up. And it doesn't drop back to zero. Like when you didn't have a tank in the building, the water age went back down to zero pretty quickly. When you do have tanks, though, it doesn't really drop down that much. It takes a while for the water age. And depending on the sizing of the tank, a lot of tanks are sized for like a peak day flow or something like that. And it takes a long time to turn over the water in the tank when you have that. Okay, so now we're, boy, things have really gotten slow here. Okay, now we're looking at pressure with the tank, and the pressures look a lot different too. The pressures stay maintained a little longer, so when you turn on a faucet at the upper floor, the pressure doesn't drop quite as much because the tank is right near that upper floor. Bottom floor, the changes are pretty minor in that particular case. So this is the kind of stuff that you can experiment with. What if we turn, and that's the kind of work that we're doing right now, is looking at, okay, what if we don't fill the tank up all the way? Let's say we only fill the tank up part of the way during day. Let's say we let the tank drain a lot more. A lot of these places, as soon as the water drops a couple of millimeters, they turn the pump back on, and that's not a good thing to do. But so we can experiment with this, and this is the kind of result you see in terms of pressure. Okay, next. Okay, then I looked at how to lay things out vertically, and just to show that it can be done, two different ways where you put the riser pipe, but it doesn't look as pretty. I wasn't as impressed. I like laying the different floors next to one another, but if you want to lay them on top of one another to help display what's going on, this is what they look like. Okay, and you can see this I think is laid out by diameter in this particular instance. Okay, next. So what happens is that the big need here, one of them is how do you build these models? Because before you could do it with a GIS, and we don't have GISs in the building. So what you need to do here is go to BIM type software. And this is one of the places where we have some amazing software where we can take the building, do the X-ray of the building, and have the material that we know where all the pipes are, where this is just something you create as you're building the building. You have a BIM model, building information modeling, and we could use it. Now that particular picture there is actually an HVAC system, not the water system, but you get the idea of the data are there. So just as we import data from GIS in order to build water distribution system models, you can import data from building products pretty easily. Okay, next. And then here just shows you some more. We have some other tools we use for plant design that are used for oil refineries and nuclear power plants and all. And again, these kind of models are great because you can extract the data quickly rather than manually building these models by digitizing them in 3D. I mean, it's really hard. So this is looking towards the future now that this kind of stuff we already have. We can actually do hydraulics in 3 dimensions and show flows and all, but it unfortunately is only based on some really simple steady state hydraulics. So what we would need to do is to link this kind of 3D technology for model building and results visualization with water gems or an EPANET-based solver or something in order to come up with the really great visualizations. I think because we try to do this kind of 2D stuff that I was showing, that's okay, it works. But if you can show things this way, it really looks good. So it's something that we're kind of uniquely positioned to because we have all these tools that work in 3 dimensions. And we've done a lot of this, I guess we actually call it 4D, you know, where it's a 3-dimensional viewing based on context capture over time. And we've done things with our flooding products where we could watch floods, you know, actually, you know, move anywhere we want to in the city and stand there and watch the flood come in and out. So it's definitely something that's doable, and it's a matter of when the demand from people who want to, you know, buy software and have money, you know, we'll have this stuff implemented pretty quickly. The devil's in the details, of course. The concepts are pretty easy. And again, if those of you who are researchers and don't have money, we'll work with you. If you want to do something that, you know, built on a 3D visualization, and you can talk to me and we could talk about that sort of thing. Okay, next. I don't really do the 3D stuff, so I'm kind of not that good at it, but we have people. So to summarize, you can do water distribution, hydraulic and water quality models in buildings with what's right on the shelf now in EPANET. So the big issues, though, that we have to overcome are easily bringing in elevation data and quickly doing that. Modeling pulse demands, like as I mentioned, I just used a random number generator to do the demands, and you know, we can do better with that. And I'm looking forward to the talks they're going to talk about, you know, hydraulic, you know, Poisson rectangular pulse models and such to generate small time scales, and tools to display things. You know, we can do the 2D displays, but we got technology out there that goes even farther than that. So that's some of the things that are needs and what we have right now. Okay, thank you. And
issues that Tom brought up was, you know, related to demand estimation, and that sort of segues into the next section on demand and hydraulic modeling. Where demand estimation and hydraulic modeling issues are important issues for premise plumbing systems. Water quantity delivery issues in a home or building can arise from poor distribution system pressure, as Tom noted, and then even into the poor premise plumbing design or changes that may have happened over time that didn't take into account the whole history of the building. The water quantity has been a major concern in building design, which has been a focus on ensuring each demand receives the maximum flow when requested. While many issues of water are more volume-based, as some of the people on this call may have noted, where you know, you just wait for a glass of water to fill, and it may take a little longer, or you know, you may take a more time-based use where shower with lower pressure may not really be desired, but you know, within reason it's tolerated. So you just take a shower for some length of time, and modeling the actual demands related to that is a challenging topic. Accurate modeling of usage patterns is critical, and additionally, models must ensure that flow rates are accurately modeled if the pressure conditions are not sufficient and for the requested demand, as was noted. Models may also need to predict and keep track of who or what is using the water. Miriam Blocher from KWR Water will now present some areas on this topic.
Yes, thank you very much. So I'll try to make it on time as well. So please go to the next slide. We've developed a demand model called SimDeum, simulation of demand by means of an end-use model. So this is a crash course in one slide to show you how it works. So an important part is that it has physical-based parameters for frequency of use, flow rate, duration of use, and they're all based on survey data. And they are all stochastic. So we have information on how often people flush a toilet, which follows a nice Poisson distribution with an average of 6. Duration of taking a shower is a log normal distribution, etc. It is a very small spatial scale, so it's really at the end use, so the tap, and a small temporal scale based on 1 second. And of course, these can all be aggregated to larger sizes. And it really follows it results into realistic demand patterns, which means both mean and variance are very well represented from the model, again on a whole range of temporal scales and spatial scales. And since we've really done this by end use, we not only know what the total water demand is, but also, for example, a difference between cold water and hot water demand. So this was being built in from the start. Next slide, please. So this is for you to read later. To the next one. So what we have done, and I'm trying to give you a couple of examples of projects that we've done that we've used this model in premise plumbing modeling. So here is a very basic EPI-net model of a home installation where you can see water meter and then up to the water heater, and from the water heater to all the hot water taps, and water meter directly the cold water taps as well. So we've taken all the different end use patterns and we've applied them to the specific tap. And then you can look at hydraulics, again, as Tom showed, and water age, and other water quality. So we've looked at temperature specifically, but also at some microbial parameters. Next, please. I would like to also apply these to premise plumbing of the in-home sewer. And I think the DrainNet model from Heriot-Watt University would be very useful. I am in contact, but haven't gotten the model yet from David Campbell, but he's willing to cooperate. So hopefully by next time I can show you some results. It's very similar, of course, to the demand side, but at this time the discharge side, we can also add temperature and different nutrient loads depending on the end use. So nutrient load from shower water is different than toilet water, for example. Hopefully we can show you some results next time. Next, please. So one of the applications is water meter sizing. The graphs show some results from what we've done together with Steve Buckberger on the Milford data, and show you the maximum flow velocities on a very small time scale. So this would help you to determine the size of the water meter. Next. And by also looking at how these sort of flows are divided over different flow rates, you can also assess the billing accuracy. As typically in lower flow rates, the water meter is less accurate. But if there's not a lot of use in that area, then the effect on billing accuracy is not that large. But it could be different depending on the different demand patterns specific for the building that you're looking at. Next, please. One thing we did is at TU Delft, Juliana Zlatanovic built a really nice model in an elevator shaft, mimicking the drinking water installation, domestic drinking water installation. And she measured for 1 year, and she did not invite people to live in this elevator shaft, but we put SimDame demand patterns on each of the taps. So there was a different demand pattern for each day of that year. Also, we introduced weekend days and weekdays. She measured temperatures. She also measured some microbial parameters and tried to relate that to water age and things like that. And the temperature model was found to be really close to what we actually measured. So that was a good validation. Next. Another application is look at demands under stressed conditions. So for example, what if there's not sufficient pressure, or what if electricity is not available, or what if people would have to be at home in home isolation. We haven't looked at that yet. So especially the pressure depending demand is really related to that 3D layout of your system, as your water heater is typically at the top floor, and if the pressure is not enough to supply water to that, people will definitely not take showers, or unless they really like their showers cold. So there is no direct interaction now, but we can really, we've really looked at what if pressure is sufficient to reach the first floor or second floor, but not the top floor. Next. Another application that we looked at is the production of light gray water from showers, and the need for light gray water to flush toilets and use in your washing machine. And depending on the people that live in the house and their behavior, you can determine what the storage is that you need, not just for a single house. You can also look in an apartment level. And in this case, we found that storage capacity of 200 liters per household would really could be sufficient to get a good reduction in drinking water demand. And rainwater did not add that much to it. But in this case, it's really nice to really at the same scale look at what is produced and what is demanded, instead of sort of per day estimations. Next. We've also looked at energy use for hot water. So again, taking into account the whole 3D layout of the system, pipe lengths, you can see how much energy is lost during waiting times, and badly insulated pipes. And this will inform you also that CO2 or how much money is required for hot water demand, also depending on the type of water heater that you install. Next. We have not applied it inside the home yet on sewers, but the paper that we show here was, when I put this down, it was submitted, but it came online yesterday. So it's now published, where we actually did use SimDeum to determine also the COD, total suspended solids, nitrogen and phosphorus, predict how that would be transported through the sewer network. And it was validated in a small area in Amsterdam, and the model and measurements looked really good. So I think there's quite some options to also scale this down or up, I'm not sure, to the premise plumbing as well. Next. So future work. I can see it would be nice to couple such a demand model with EPANet to make much more use of its stochastic nature. What I've done so far is look at 300 or whatever types of deterministic EPANet outputs, and then look in MATLAB and try to make some sense of variations in water age and things like that. It would be nice to directly be able to see that. And also, I think a coupling with EPANet could really enable pressure adjusted demands, instead of doing this by hand And as Jonathan also said, well, if it's just a toilet flush, it might take a little bit longer to fill that cistern. But the total demand will not change. So that sort of thing should be, I think you should be able to do if you have a direct coupling. What I would like to do is also apply this in drainage models, in home sewer models, and to define some sort of a standard drinking water installations for domestic but also non-domestic that we could all use for our publications and use as a good reference. Another thing that we're doing is we build SimDay in MATLAB, but we're translating it into Python, and we'll put it in the open source community in GitHub by the end of the year. So open for everyone to use. And that's it.
Well, thank you, Miriam. That was very interesting. Just because we have a little bit of time, I'm going to ask hopefully 2 quick questions that came through the chat. First one was for the demand data appears to come from Holland. Is that the real source? I thought the data for the model came from the North American Residential and Use of Water Studies. Thanks.
Yeah, so I built the model with Dutch data, but we did apply it also to the Milford data and tried to find more information also from Peter Meyer's publication on water demand and household surveys of how often people use their baths, etc. So as soon as you have that type of information, you could apply it to each country and make it specific on cultural behavior or types of appliances that you would have. So.
Thanks. And the second question was, are there any links with the AMRs, the automatic meter readers?
We're looking at that. So if you have automatic meter readings with high enough frequency measurements, you might be able to determine some of the input parameters more easily or even more realistically than by surveys. So we're looking at that and how to do that. But when I built the model in 2006, I didn't have any AMR data, but it's an exciting new research theme.
Okay, great. It looks like we're about ready for the next speaker. So there's one more question, but we'll circle back around at the end. So the next topic area is on water quality issues. Water stagnation in homes and buildings can lead to water quality issues like Legionella, corrosions of plumbing materials, disinfectant loss, or byproduct formation. As Tom highlighted, we just from the simple example of water age, we can see the impact of that. Water chemistry changes over time and is also impacted by what it contacted within distribution systems and premise plumbing systems. Modeling these water quality issues may also require tracking of multiple components or involve other characteristics like temperature. Within 1D water quality models like EPA net, assumptions about flow dynamics may not hold. Specifically, there's no mass dispersion and is limited to first order kinetic reactions within premise plumbing systems. Modeling water quality requires knowledge of both usage patterns and other characteristics of that premise plumbing system, like plumbing material and layout, and the water quality entering the system. Michel Prévost from the Polytechnique Montreal will now present on some premise plumbing water quality issues.
Okay. Well, I'll try to give you an overview of what I've been working on, which was requested of me, but also general thoughts about water quality issues and why they can be drivers for these modeling tools. As we just saw, they are drivers, these tools for the drivers such as meter accuracy is certainly something very practical, but water quality is a bit more difficult to define for these models. Next slide, please. So I'll look at an overview of my research, but I'll try to summarize the major health outcomes from water quality losses in distribution system, looking at lead release, microbial contamination, and hydraulic issues in large buildings and healthcare facilities, and how they actually cause disease as examples of why controlling hydraulics in some of these buildings, especially in the hot water systems, is so critical. By no means it will cover all water quality issues. I'm not touching, for example, on nitrification for chlorinated system, which is a real issue, but for the 9 minutes left. And I'll touch on the gaps in the application and development of modeling tools that I saw at this point in our exchanges. Next slide, please. So, oops. So we know that distribution systems are a significant source of waterborne outbreaks. We kind of relate that to breaks, negative pressures, intrusion, ingress. But we know that there are health impacts of non-acute contamination events, and there is no reason not to think that some of these issues are not present in these large buildings. And there are numerous studies on intermittent flow that show such health effects. Backflow siphonage is certainly an issue in these buildings, and ingress, although the work has been done mostly in distribution systems, is also a concern in terms of causes of waterborne outbreaks or disease. Next slide, please. With the NASEM report last year, which most of you are aware of, we all saw the figure on the right, which shows the etiology of drinking water associated outbreaks in the US for the last 40 years or so. And the striking part is that it goes down over the years, but there's this black Legionella contribution that grows from 2001 to 2015 on this graph as the main contributor of drinking water associated outbreaks. And NASEM came out with a very scary estimate of the non-outbreak related numbers, which are most probably community acquired in hot water systems and cooling towers. And it begs for a better control of our systems. Most importantly, these infections that are related to biofilm organisms, way more so than fecal contamination, which was our prior focus in many of our studies for modeling, are now driven by things like NTMs or Legionnaire's disease. Next slide, please. So I'm not going to have a slide on the health impacts of lead. I just put a couple of figures here to help you think about what we can do with better prediction of the impact of water age. You can see here results on a school study published recently showing the lead concentration going down with flushing from first draw, second draw, 30-second, and 5-minute flushing, going right back up after 30 minutes. So this begs for the question of what can we do in these are large systems to minimize by improving the hydraulics and minimizing stagnation, acknowledging that part of this is at the decimal point where it is very difficult to reduce water age. Now, it is different in residences with lead service pipes, and certainly things like looking at the impact of water conservation devices on the increased stagnation in lead service lines leading to higher exposure is a main concern of mine. Next slide, please. Another shot showing red dots. This is all in one single building concentration after 8 hours of stagnation in red, and in yellow after 30 minutes of stagnation. Very obvious that stagnation brings very, very high values, and most importantly also increases the particulate formation and passage through the drinking water. Next slide, please. So I've been working a lot more on pathogens in the last 7-8 years in large buildings, identifying niches of pathogens in hot and cold water that actually drive the infection risk. Most of this work was done in hospitals with cases, looking at the role of aerators as a vector of infection, looking at the impact of material on the resistance of Legionella in biofilms to disinfectants such as chlorine. Looking at optimized thermal control regimes, which is basically balance your system and put it in control. Looking at unintended consequences of water energy conservation, redesigning the sink environment to prevent neonatal infections. Again, quality at the tap, but also at the in the sink environment and drain and surfaces as well. And most recently, actually, the last 3 weeks of my life has been COVID recommissioning, writing guidance and participating in various initiatives. And when you come to commissioning, a bit like the Virginia story, there's very little science on how we can deploy to support how we can best deploy flushing in a very large number of diverse buildings. Finally, impact of materials and pathogens in host, and I'm always trying to bring this back to QMRA to see which health risks are more significant and where we should focus. Next slide, please. So a couple of slides to show you, give you some thoughts. There was a nice slide before from another presenter showing that buildings are complex. Here I'm showing a very simplified diagram of what the hot water system is. The bottom red rectangle shows the main recirculating line system. The one just on top would be horizontal or vertical risers, distributing pipes, and most importantly, there's this distal part, the tertiary loop and return, and this last little part that gets no recirculation. So keep that in mind for the next slides. Next slide, please. So now, there's why this is from the NASAM report. We got our hands on tens of thousands of data points from a German colleague who just finished a study. And I'm showing here the percentage of Legionella positive samples exceeding the German standard as a function of temperature ranges. And you can see that this percentage goes down and there's a breakpoint around 55. The interesting part here is that the three symbols are the flush samples, so water that's not been stagnant, the recirculation in red circles, but the little triangles are the really interesting part. When you do maintain temperature throughout a system right to the distal system, you really bring that distal part, you really bring down these numbers. So again, this is a call for why it's important to master hydraulics in hot water systems. Next slide, please. On the other hand, here is a temperature profiling study that we did also in a hospital where there was an outbreak on the 7th floor. You see this little 7 numbers. These are temperature profiling coming in and in the return loop for hot water systems. And you can see at the end of these little blue arrows that you have a 34 degrees C and a 39.3 degrees C and 36.8 depending on the time of the day. This showed that for this hospital, a deficiency in maintaining proper recirculation, balancing the system basically caused an outbreak, stressing the importance of with very simple tools of balancing the system. Next slide, please. Okay, next slide, please. Oh, good. So again here, temperature profiling. On the top, before any intervention to balance the system, and on the bottom, after these interventions, and you can see the red line is 55 degrees. You turn on your tap and you measure temperature as a function of volume. Before, it hardly ever reads 55 degrees C. After, it does more quickly. And on the right-hand side, you see what it did within weeks on the percentage of positive Legionella pneumophila samples, but more importantly, what it did in terms of concentrations, since infection risks are related to concentration, obviously. Next slide, please. So the NASM came out with a really nice table, I thought, and on what we can do to control Legionella, and I put in red, manage the hydraulics. And what came out for building water systems in blue is that for large institutional buildings, green buildings and household, managing hydraulics is really the key to control Legionella. And the little red X means that green buildings with water conservation actually can work against the control of Legionella. So again, hydraulics being at the center of our focus. Next slide, please. Okay, last case study to give you an idea on a lead school case study we were involved in 2 years ago. Very low demands you're seeing for 200 kids, a peak demand flow that's very low. The school, when open, was subject to a boiling advisory that lasted for about a year. And we had to implement continuous flushing at the tap to bring back the school under compliance because it was very high in total coliforms and HPCs. And obviously for these really good systems in terms of conservation, the ability to maintain chlorine residual is really difficult because of the way we design these systems with large volumes still and with spread out points of use throughout the school. Next slide, please. So my last slide, I had a couple of ideas on what we could do with these models as they are being developed. I think they need to be used to adjust operation to minimize the release and the growth of pathogens, and targeting hot and cold water systems, and including the impact of materials and varying stagnation patterns, which is already in the way. I think it's critical to understand if and how much residual can be maintained in large systems. The Netherlands doesn't use residual in distribution systems, but we do in North America, and we need to understand what can be done. Assess the risk of water and energy conservation measures, especially when we retrofit existing buildings. Review the design of new buildings to avoid extended stagnation water quality losses resulting from the desired low water demand, and assist building operators in siting of automatic flushes. And I would make the case that one of the really good thing about the Dutch initiatives that Miriam was talking about is she has worked in several instances to try to relate this to the QMRA models. QMRA models are not perfect, but they give you a relative risk that can be very, very useful to decide where to act in large building to reduce health risks. So that is it for my presentation.
Thank you, Michelle. Any questions, please send them to the chat, and we will try to touch base at the end. And we'll move on to the next session, which is on more of the practical side, the design and regulation issues associated with building, building buildings. So many regulations focus on the quality of water produced at a water utility, and many building codes focus on ensuring adequate supply of water into the building, namely pipe size or material. System-wide modeling has been used for years to help understand how water quality changes within the distribution system. In recent years, more attention has been given to the impact of the building and its characteristics on water quality, both in large buildings and homes. Modeling tools may be able to support architects or other building planners when designing plumbing systems, both from a water quantity as well as quality side. Gary Klein from Gary Klein & Associates will now present in this area.
Thank you. Good morning, everyone, or whatever time it is. So let's just get started. Next slide, please. What are we aiming for is the topic. Where did the pressure go? Why does it take so long for hot water to arrive? How do we increase customer satisfaction? And what does this mean for premise plumbing modeling systems? Next slide. Water consumption is not what the models currently say it is. Virtually all of the codes and standards in the United States are based upon consumption numbers that date back to 1950-ish. And as you can see, since 1980, flows and flush volumes have reduced practically across the board. Next slide, please. What are we aiming for? People want the flow of flowing water. They want the water flowing from their showers and faucets to feel right. They want their toilets to flush first time every time. They want clean clothes, dishes, and bodies, and they want the service of hot water as efficiently as possible. And it does not make sense to discuss efficiency until you've provided the desired service. So as a comment to some of the slides that we've seen already, where green buildings don't perform well is they're not focused on the service, they're focused on the rules for green buildings, they're focused on the flow rates, not the service of hot water or cold water, and that needs to be fixed. Next slide. This is a typical simple hot water system. It could be in any building. Next slide. And this is a typical central boiler hot water system where you've got long distances between the source of hot water and the fixtures involved. And again, it's typical for apartments or other large buildings. Next one, please. Much of my work has been focused on hot water. And what I've learned over the last 25 or so years is that people want hot water now and they don't want to run it on their shower. And hot water now is dependent upon having a source of hot water close to each fixture or appliance, and it must be hot enough to use as hot water before you turn on the tap. Continuous is not running out while you're in the shower, and it turns out the problem from our evaluation is not the first shower or the second shower, it's the third shower. The third long event tends to be the one that loses temperature, and people complain. There is one other thing that people would like to have that's not on here. They'd like a parental control switch for their children's showers. Next slide. So next question, where did all the pressure go and what we can do about it? Next one. Let's look at a second floor shower. By the way, in the United States, most of our water heaters are located down, not up. And so they tend to be in basements or in my case in the garage because we don't have basements. And let's just assume that you've got 80 PSI of street pressure. You got to go up in elevation, you lose a little bit per foot, you end up with about 9 PSI of pressure drop. A tub shower valve in the United States turns out to have a fair amount of pressure drop in it, and I picked 11. It's within the range of what we've measured. And then the losses in the piping are some number. I picked 20 to make this example work right. It depends a lot on how you've laid out your hydraulics. And so you end up with a residual pressure at about 40 PSI at the shower head. Why did I pick 40? It's because flow rates for shower heads in the United States are rated at 80 PSI. And so if you have a fixed orifice shower head, the flow rate at 40 PSI will be 0.7 of whatever that flow is rated at 80. At 20, it's 0.49, which is 0.7 times 0.7. The real number is half the square root of 2 times the number in the pressure. So the problem is that if you didn't like 2 gallons a minute at the shower at 80 PSI, you're not going to like it if it's either 1.4 or about 1 gallon per minute. That's why people complain. We can do things about it. Next slide. Why does it take so long for the hot water to arrive? Next one. Well, over 20 years ago now, we learned that it takes roughly 1.5 to 2.5 times the volume of water that is in a given pipe before hot water of 105 or hotter comes out the other end of it. It doesn't matter if the source is a recirc loop or a water heater. It takes longer than that if you're starting with a cold water in a tankless water heater. But assuming you have hot water somewhere at the beginning of the event, it takes 1.5 to 2.5 times the volume of water in the pipe. For our purposes today for estimation, we can assume it's roughly twice. So what we've learned in research that I did with Jim Lutz in the last couple of years is that a huge number of events in a daily routine don't actually ever reach the fixture in question because the volume of the event is smaller than the volume in the pipe. And we have to figure out how to get that effect into our modeling. Next one, please. So how do we increase customer satisfaction, which is my key interest in all of this? You have to figure out how to reduce the time to tap. We have to reduce the pressure drop, and then we have to install pressure-independent faucet aerators and shower heads. So let's see here. Sorry, next slide. I'm going to pick from a few of those topics because of limited time today. When we have a chance for a longer conversation, I'll be happy to go into detail. We have it. So let's reduce the pressure drop. Next one. We have a lab. I've had a couple of labs over the last couple of years. The one in Downey is a teaching room at the Southern California Gas Company. They've converted into a wet room, and they let me come in there and teach classes and do experiments on things. That's on the left. The one in Arcata I set up on my own. We've got pressure measuring equipment. We've developed a method of test for measuring the pressure drop in the pipes and the fittings. You can see that in the middle of the slide. There's a rectangular spiral of whitish pipe that's CPVC, and I'm in the background holding the pipe for the guy doing the work. Next slide. We've also measured the pressure drop through tub shower and shower valves. In all cases, we try, because I couldn't get it from the manufacturers, so I just went to my lab and measured a whole bunch of them. It turns out that in the store, if you see 20 or 30 models from a given company, there's probably only one shower valve or tub shower valve behind the wall. And so that makes the measurement relatively straightforward. And so what we found in the case of the pressure drop in pipe and fittings, we now have 50 samples for 1/2 and 3/8 inch nominal pipe, copper, CPVC, and PEX. We've measured the pressure drop for those at 2, 4, 6, 8, and 10 feet per second. In the case of and we have a range ranging from 0 extra pressure drop through a bend to as much as 6.5 PSI through a bend, depending on the material and depending on the nature of the fitting. And then for shower valves, we measured that at 0.5 GPM increments to see what the pressure drop through the valve would be at a variety of flow rates. And we have numbers that are the best and the worst are roughly 2 to 1 at any given pressure, at any given flow rate. The next. This shows you the shower valves. And I didn't name them because I'm not trying to embarrass anybody, but the ones that say only, which are the dash dot dash and the dash dot dot dash lines, are shower only valves. The others are all tub shower combos. And so the point here is that we have to pick these carefully to get the least pressure drop at the shower. It is my hope that someone in Europe will start sharing us valves in the United States so that I can run tests on them just like this, or you can do it there, so that we can see the differences. There's large restrictions. These are all the 1016 compliant valves for anti-scald in the US. Next slide, please. So I think we have to think about installing pressure-independent faucets and shower heads. Next slide. And my question to you is, which one do you want? Do you want the normal pressure curve aerator, or do you want the green or the orange lines? Next slide. How does this affect modeling? Next one. This is what many of us thought for many of our years, that this is what the flow patterns would look like. These sort of sine-ish wave curves. Next slide. But there's lots and lots of events. Notice how many of these are faucet events. These are the really short ones as best we can tell. The next one. And Peter, these numbers come from data that you developed many years ago. The actual daily hot water loads tend to look like this, as was shown earlier. Lots of little spikes. Next one. So in the models, as I said earlier, nothing flushes or flows at the rates when the plumbing models were developed. The plumbing mathematics for pipe sizing were developed. Hot and cold events are practically random. Yes, there are patterns, but there's huge variation. Distribution system performance depends on a variety of things. And when we model things, we have to assume we cannot predict who's going to be the occupants or what their schedules are. So I think we need to design plumbing systems that work well independent of that. The next slide. Premise plumbing models do need to be revised. Very few steady state uses of water. There are virtually all this intermittent stuff. The calculations need to be based on modern pipe and fittings. There are no good data for the modern fittings in the tables. I've got the best data set I'm aware of at the moment because I've actually measured it in a consistent manner. We need to account for the waste of water waiting for hot water to arrive for those events that require it. Short events don't actually seem to require hot water. They require water of some temperature. We should think about that. The next slide. Energy models currently assume that all hot water that leaves the source arrives at the fixtures. It's not true. You can read all about this later. Next slide. Energy models need to be revised. We need to provide an equal level of hot water service at each fixture in order to properly compare the performance of alternatives. Currently, we penalize systems that try to deliver hot water efficiently as opposed to those that don't deliver it in many cases at all. The next one. And then given human nature, I think it's our job to provide the infrastructure that supports efficient behaviors. Thank you.
Thanks, Gary. So that was great. That showed a lot of the practical issues associated with building design, and definitely interested in the data sets you've collected. So the last session of the day before we do some wrap-up activities is related to the future direction and needs. And as all the speakers up till now, highlighted the complexity of premise plumbing modeling, and it relies on, plumbing layout, usage pattern, and then, more specifically chemical and biological kinetic data, if we're going to get to that level, or temperature modeling. And it requires some kind of available modeling tool. Although capable tools like EPANet may not be enough to capture the complexity of premise plumbing systems, at least on their own. Full rendering of 3D CFD modeling may be overkill, but a multi-species 2D model with dispersion may improve modeling of various water quality issues. And when coupled with a probabilistic agent-based demand estimator, as previously discussed, we may have a valuable tool for modeling premise plumbing systems. And now our final speaker, Walter Grayman, will discuss how we as a community can move premise plumbing modeling forward and their associated tools into the future. Thanks.
As has been said before, the task committee has a dual purpose, and one of them is to try and establish what has been done, what is the state of the art. But just as important, it's to look at what needs to be done. And each of the speakers has been very good in terms of addressing both of those points. The talk I'm going to give is really a look at a kind of a straw man of what we may want to do. And some of that's been covered in some of the past talks. This is called Vision for an EPANet Premise Plumbing Modeling. The purpose of the presentation, the things I'm going to try and cover and we should be discussing is the applicability, the need for a specialized EPANet, or as Tom indicated, other package for modeling premise plumbing. Looking at what changes may be needed in the existing software when modeling premise plumbing. Should a special purpose software package for modeling premise plumbing be built? Would anyone use such a package? And what should such a software tool look like? Next, please. When we look at making changes, there's two general areas. There's first of all the engine, which is the modifications in the way that EPANet or other software simulates the hydraulic and water quality behavior. And there's the interface, which is modifications in the interface and the integration aspects of the software. And we do need to address both of those. Next, please. Some of the areas in terms of engine modifications to support premise plumbing, demand representation, which Miriam talked about and others talked about. Some of the hydraulics, dispersion, laminar flow, operation of premise plumbing fixtures. And as Michelle mentioned, talked about water quality components. Next. In terms of demand representation, again, Miriam covered much of this. EPANet currently supports fixed patterns and to some degree pressure-dependent demands. The latest, more experimental version supports that. In premise plumbing modeling, additionally, it requires stochastic demands, very fine time scale patterns. It takes 20 seconds to brush your teeth. And hybrid models, which again has been mentioned, which are both volume and pressure dependent representation. So for example, a washing machine or a toilet that fills to a fixed volume, but the rate at which it fills is dependent on pressure. That's a different type of demand than what EPANet currently supports. Next. In terms of hydraulics, some of the areas, laminar flow, low velocity conditions, dispersion, non-advective transport through the piping system, highly intermittent flows, as we've seen in several of the slides, where essentially there can be a 6 or 8 hour period where no flow is used in a system, and operation of premise plumbing components. For example, I don't know, I'm sure probably Gary does, how a water heater works. Is it a completely mixed tank, or is it a FIFO or LIFO type system? And we need to know that if we're going to be able to model it. Next. And of course, water quality representation. We need expanded multi-species modeling of temperature, and temperature is not currently done in EPANet. It is done in some of the commercial packages. The ability to model Legionella, viruses, bacteria, lead and copper and corrosion, and other water quality parameters. And obviously there's additional research and really basic research and understanding needed before we can effectively model those. Next. On the other hand, there's the interface modifications, and I show there is the standard EPANet GUI. What needs to change, or what would we like to change? As Tom indicated, yeah, we can use the present software packages, but it may be nice if there were some changes to make it more friendly to modeling premise plumbings. What components are needed in a premise plumbing model? How do we display it? 3D representation of premise plumbing. And again, as Tom mentioned, integration with CAD and BIM software. Next. So here is at the top of the slide is the standard EPANet palette of components. And again, we can adapt things. We could use a tank to represent a water heater. But maybe it would be nice if we are going to be modeling premise plumbing that we have a specific premise. So bathtubs, toilets, washing machines, etc., with each one of those having the characteristics specifically of that premise plumbing feature. Next. Display and integration. Again, I'll reference back to what Tom talked about. We do need to reach out to the BIM, the Building Information Modeling, and the CAD communities to find out what is available, determine what is needed, and develop a plan to support premise plumbing modeling so that we can easily build a premise plumbing model rather than doing it by hand, and then be able to display the results in an effective way. Next. We've heard about it, and I think over the course of the next several months periods where task committee is working, we want to identify the potential applications for EPANet PPM, I will call it, or again, a commercial package. Assist in the design of premise plumbing, improve the operation of premise plumbing, and Gary talked very much about that. Investigate the vulnerability of premise plumbing to contamination, understand the water quality processes in premise plumbing. And there are many more that we're going to try and explore within the task committee. Next, last. So some points for discussion, and these are not meant for today, these are meant for the future. Is there sufficient interest in having a version of EPANet or a commercial package that is specifically targeted towards premise plumbing modeling? Should this be a commercial or a public software, or should it be a hybrid? Are we looking for a research tool or an application package? Application packages need to have a very vibrant GUI and a display package. Research tools, they can be a little less finished. And who needs to be involved in the decisions and the process? So I think hopefully we're back on schedule, and I'll turn it back to Jonathan.
Thanks, Walter. That was great. That did catch us up. So our next point of discussion is the participant survey, where Steve Buckberger will now summarize what was provided back to us in the questionnaires.
So thanks very much, Jonathan, and good morning or good day to everyone. Enjoyed the presentation so far. We've been going almost an hour and a half. I have just 6 slides to share with you, and I'm going to touch on the highlights of the survey that was distributed back at the beginning of the year to about 40 people across the planet. And we asked you to consider 4 questions, and the questions I have listed here. Number 1 was what you thought perhaps were the most important research and development needs to support computer modeling for premise plumbing systems. The second was, could you identify areas where the premise plumbing models would be usefully applied? The third question was, can you believe that? I still have a landline phone. The third question was, what are the main applications or the main challenges rather in adopting the premise plumbing models in practice? And then last, we gave you an opportunity to add any additional thoughts that you might have. So it turned out that in the ensuing 3 or 4 months, we got 22 responses, 219 total ideas, and I'm going to talk about them briefly in the next 5 slides. Now, just to give you a warning, I certainly can't go into all the detail, and there's a lot of great ideas. And so there's a little word cloud here on the side that's based on all 22 pages of responses. And we're just going to touch on some of the key points that came through with this response. So next slide, please. All right, so one of the underlying themes, one of the maybe perhaps an undercurrent was some recognition that we've got a collection of individuals across the planet that have a lot of experience working with water distribution systems. And we have a good history here, probably 20 or 25 years, where we've applied some and developed and tested and validated some models. And yet we're moving into an area that's kind of uncharted, and it presents some new challenges to us. And in fact, there's some pretty dramatic distinctions between a water distribution system that we're more accustomed to dealing with and a premise plumbing system. And so this table here just briefly highlights perhaps 9 of what some of those distinctions might be. And I'll just touch on a couple of them. For example, number 2, with the topology, most of the time in a water distribution system, we're dealing with a looped network. In contrast to that, most buildings have premise plumbing systems that are branching pipes and include many stubs. Pipe placement is different. It's in the dirt, it's in the ground with the distribution system, it's in the walls with a premise plumbing system. Flow regime, we've talked about this already. We've mentioned this briefly this morning. The presumption is that in the water distribution system, we're dealing with plug flow, turbulent flow. Whereas when we get into a building, we're talking more about the laminar type flows, stagnation, maybe the transition through critical flow to turbulent flow. So we have a much more diverse mixture of flow regimes. And that has important implications, frankly, for how we model water quality, because it has an impact on the velocity profile in the pipes. The demands, there's been some discussion on demands. Generally in the water distribution system, the demands are considered to be more or less a continuous stream, whereas certainly inside of a building, it's an intermittent random pulses that we're dealing with. Stagnation, relatively rare in a distribution network, is very, very common. In fact, even during the peak period of the day in many buildings, it's not unusual to have stagnant conditions where no one is actually using water. The design flow conditions are quite different too. Fire demands are oftentimes the driving criterion for a distribution system, whereas on the building side, we'd look at something like a Hunter's type curve, which is based on the 99th percentile of the expected peak demand. Temperature, not a factor, not a consideration at all in water distribution systems, but as we have already heard this morning, really important. In premise plumbing, we have both hot and cold water systems, and they have important distinctions and so forth. And then even the fixtures themselves, in a water distribution system, we have a lot of what we might consider industry standards for what might be used. But in contrast to that, in a premise plumbing system, we've got, frankly, a wide universe and a broad assortment of appliances. And I had to chuckle too. In fact, one of the responses that came in called them kind of a galaxy of gizmos that are out there, that are all part of how we draw water out of the premise plumbing system. Okay, next slide. So the remaining slides, I'm just briefly going to touch on the four questions now. And that was the first one, of course, was research and development needs. Three major themes that just bubbled to the surface here. One was we have to get just a better understanding of the water quality dynamics in premise plumbing systems. And this is a complicated problem. We all recognize that. We're talking about water chemistry issues, pipe material issues, microbiology, different flow regimes, intermittent stagnation, and so forth. So, it's something that we have to focus on if we want to get a good understanding of predicting water quality changes inside of a building. And then that goes hand in hand with getting a better characterization of and being able to model water demands. Now, we've made great progress in this area, tremendous work by the Dutch group and Miriam. And so we have to find a way really in the third case, the third bullet item is to somehow combine these two, improving our understanding of water quality dynamics, driving it with a water demand model to develop some kind of a user-friendly network type model, as Walter just mentioned, perhaps an extension of EPANet to premise plumbing systems. I will tell you, those were really the three main themes that came out of the 80 needs that were identified here from question number 1. Next slide. So in the second question, there were actually 64 different applications that were identified. But it seemed as if they could largely or generally be categorized into two groups. One group would be perhaps applications where this premise plumbing model would be a tool to inform building design. And here we would have the link back to the MEP, the mechanical, electrical, plumbing components of BIM software. We've talked about that. I think the planets are lining up. The timing is right. We can really make a move now to try to combine a premise plumbing model with BIM software. And we could work on problems like optimizing pipe sizes and layouts, minimizing cost, energy use, et cetera, and preventing code violations, backflow, and identifying potential water quality problems before they arise and avoiding them. And then the second category really was using it as a tool to inform building operation and maintenance. Can we identify hotspots for sample collection, water age, stagnation issues, flushing programs in the event that we have to go in and decontaminate a building. Perhaps vulnerability assessments came up. And even the situation we're dealing with right now, as Michelle mentioned, many buildings have been vacant for a long time and we have to go and restart them. Here's where perhaps a premise plumbing model would be helpful to identify the best way to start up a water supply system in a building again. Next slide. All right, so question number 3 was main challenges. And here I thought there were 60 different challenges identified. So we recognize that there are lots of obstacles. Of course, this makes it a worthy problem, doesn't it? And but the one that was or two that really were identified most often was, is this something that would be accepted by the plumbing engineering community? Is this a product that we could convince them that there's value here and that they would endorse it and be willing to want to use it and apply it? And going hand in hand with that were concerns about cost. And we're talking about the cost to acquire the software. That is, if someone has to purchase it. So, for example, EPANet is public domain. There is no cost, but we don't know what this next version might look like. What's the cost to actually use the model? In other words, if a firm decides they want to apply it, how much time does it require to come up to speed and actually to run the program? And then based on recommendations that might come from the program, what's the cost to implement those recommendations? Are they reasonable? So lots of issues surrounding the cost. And then the third was just overall this general difficulty in creating and sustaining this reliable, user-friendly product. I mean, in a sense, we're kind of after the holy grail here for premise plumbing. We'd have to conceptualize what this would look like, combining water quality and water demands, code it up, calibrate it, validate it, and apply it. And somewhere along the line, we have to find the funding to be able to sustain and support an effort like this. So it's a worthwhile challenge, and we've got a lot of, I think, very knowledgeable folks that are interested in working on this problem. But it really is our sort of analogous to the TOE in the physics community. We're after kind of the theory of everything, the TOE, the theory of everything here in this case with this premise plumbing model. All right, final slide. And this was additional thoughts. It turned out about 15 folks wanted to add some additional thoughts, and I call those the WOE, the W-O-E. And what I mean by that is generally words of encouragement. So very heartened to see everyone recognize this was a great opportunity for collaboration among agencies and across disciplines. Certainly, this is going to lead to some journal papers and some joint research proposals. Even opportunities to produce state of the science material that we can use in the engineering curriculum. I mean, after all, there's really not a lot of work in the engineering curriculum right now in this area. It's perhaps not viewed as quite sexy enough, and I think there's certainly a lot of need to revisit that and bring it back into the curriculum so that the next generation of engineers knows how to properly identify and solve these problems. And then even recognition that this is a wonderful opportunity to connect with the building energy simulation crowd. There's a whole other group running around out there that spends a lot of time in building energy simulation. And that has a lot of overlap in the Venn diagram with this problem here. And we should be interacting with that group too. So I don't know how I did time-wise. I think I might be a little bit ahead of schedule.
Yeah, you're good on time, Steve.
All right. So I'll actually wind down then sooner rather than later. I think I've covered the 6 slides and touched on. I will mention I'm in the process of consolidating all 22 pages so that we'll get those bound up so you can see the full reporting from all the participants, and you can draw your own word clouds if you like and your own conclusions. And we'll make that available to all the participants here in the next couple of weeks. Thank you.
Thanks, Steve. That was great. And your last slide, I think, is a great point to highlight the collaboration. As was mentioned at the very beginning, this is part of the ASCE, the Civil Engineering Society. We have some people who are on this call who are also part of the new committee for the American Waterworks Association, specifically for premise plumbing issues. So if you're not aware of that, you can reach out. We can get you connected with Simone and or Alex Mafidi. And maybe if we have a little time at the end, they can give a little overview for those people as well. But I just wanted to, I was going through all the questions on the meeting chat. It looks like some of them have resolved themselves, but one of the ones from the very beginning was for Tom Walsky, and it was sort of how common are roof tanks, tank systems in the U.S., and can additional minimal treatment be applied within the tanks to resolve quality issues after long-term unintentional storage, a la the COVID quarantining right now?
Okay. We don't have a lot of storage in buildings in the United States, but we're working in China. They have rooftop tanks everywhere, pretty much, and they have terrible water quality. But they refer to this, instead of premise plumbing, they call it secondary water systems. And yes, that's kind of stuff we're going to be testing. Is, can you really afford to have booster disinfection in these tanks, or do they stratify as part of the work we're doing? And also just how to operate them, it becomes real issues, because they do have so some major losses there. So it's not just the U.S. where this is happening. And the thing is, they actually have some regulations coming down the pipe about this, and they're trying to pass the responsibility for running these systems off to the water supplier and not to the building owner. And so that's going to be the regulatory environment there is more demanding of this kind of stuff than the U.S. I'm waiting for the U.S. to try to come up with some regulatory requirements, because that's what it's going to take to drive any money into this. Otherwise, it's a bunch of us researchers talking to one another. Okay.
Thanks, Tom. And Morris raised a point. I don't know if this was specifically to any speaker, but I'll just I think this is a good point to ask the question of, as we're thinking about where to go next, but can existing petrochemical plant piping models offer any tools that we could use in premise plumbing modeling? I don't know if any of the speakers want to speak to that, or we can just leave it as a discussion point for future meetings and a question that we just ask ourselves. So I don't know if any of the speakers had any thoughts on that, but.
Well, as I mentioned in my talk, we do a lot of this kind of stuff, but it's mostly just like a peak in other parts of the company, so I don't get involved with this. But we do a lot of this under the BIM and CAD parts of our company, and mostly, though, they've tied it in with just some simple steady state peak flow stuff, like based on fixture units for pipe sizing, as the old Hunter methods.
Okay. All right. Well, thanks. Like I said, I think a lot of the questions have been resolved in the chat, so you can all see that. I think, and that's a good thing. I think we're going to try to pull those out and also share that with the group, just for the record. But I think we're pretty good on time, so I don't know if Simone or Alex, if you're on, if you want to, have a couple minutes to just introduce yourselves to the group for anybody that might not know.
Yeah, definitely. I can do that, and maybe Alex can add on to what I have to say. So thanks so much for this fantastic series of presentations. My name is Simone Triantafilidou, and I'm an environmental engineer with the U.S. Environmental Protection Agency. We have a parallel committee to this, so this kind of task group is the premise plumbing modeling group, and we have a parallel effort going on under the umbrella of the American Water Works Association, or else AWWA. For those of you who are not aware, we call our committee Premise Plumbing Beyond the Meter. We started in late 2017, basically as a subcommittee under the Distribution Systems Committee. We had around 50 members or so from more than 30 organizations representing academia, consulting, industrial partners, and federal and local governments. And what we realized was that there was really great interest in focusing on premise plumbing issues, and there wasn't a lot of conversations under AWA specifically on premise plumbing. So we ended up becoming an independent committee with AWWA recognizing the importance and kind of the distinct characteristics of premise plumbing. So we are now a separate committee. We now have more than 80 members. Some of them are part of this conversation here, and we welcome any other members, any one of your audience, Jonathan, that is interested in participating. You can send myself, Simone Triantafilidou, or our vice chair, who is Alex Mufidi, an email, and we will be more than happy to connect you to the AWA volunteers who can through which you can submit a form to become a member of our committee. But basically, we have bi-monthly calls, and our next one is in June. We would welcome any conversations or updates from you guys. And in fact, we had Jonathan give us an update in our last call about this task group and your efforts. So we're happy to collaborate in any way, shape, or form as you seem fit, and we would welcome continuing these conversations.
All right, so thank you, Simone. So as you know, we're actually really good on time. Many of the comments are, as I said, sort of continuing to be answered as they come through. So I've sort of lost track. If there's any really outstanding issues, then please sort of bring my attention to that. But I guess we can maybe move on to Regan to get ahead of schedule, and then if there's any outstanding questions, we can sort of circle back before our noon cutoff. So Regan, if you're ready to go, we can talk about what the future is.
Sure. Thank you, Jonathan. And thanks to all of our speakers so far. It's been a great series of talks, and I know I've learned a lot, and it's really exciting to see what's going on out there. And then our next step is to think about how we can keep our momentum going and continue and try to build even better collaborations to achieve some of these goals that we've set out for ourselves. So as you might recall, we originally had planned to have a 2-day workshop, and we were going to have sessions that followed the topic areas that we discussed today. So we were going to have, instead of just one speaker under each of these topic areas, we were going to have several speakers and then time for discussion after that. And so given the uncertainty in the COVID situation right now, we're hesitant to plan another in-person meeting date. And so what we'd like to do is propose that we continue to have a series of webinars, and we would have each one focused on each of the topic areas that we discussed today. So we could, for example, have one that would focus on the water quality issues, one that would focus on demand issues, and so forth. And then for each of those webinars, we'd have several speakers and time for discussion. And so that's what we'd like to propose, and perhaps we would hold these one every 2 months. So it's April right now, so we could have the next one in June, and then every 2 months after that. So this is our proposal to you. We'd love to hear your feedback. So if anybody wants to chime in on the chat or to send us emails later to say if you agree with that, potentially we could have an in-person meeting sometime in 2021, but we'll have to just wait and see about that. So one action item is to ask everybody to give us feedback on that proposal for holding meetings every 2 months. Another action item is if you know anyone else who really should be involved in these discussions that we're having, please let us know. And when we're meeting by webinar, it's a little bit easier to have a slightly larger group involved, so we can certainly open it up to a few more people. Next, we did ask everyone to participate in the survey, and you heard Steve mention the results of that so far. If you did want to participate in the survey and you haven't sent your form in yet, please go ahead and send that back to Junasuk. He sent it out to everyone in an email, I believe on April 1st. So if you can look back and find that form, fill it out and send it, and we'll include it in those final results. Next is that we do have a Google Shared Drive set up that we will be opening up to all of you who have participated. And on that shared drive, we'll include the presentations from today, the recording, and any other materials that we're going to be sharing. For the original workshop, we had asked folks to submit issue papers, and several of you did submit those papers. But if anyone else would like to submit a paper that just shares information about what you've done so far in this research area, or your thoughts on the future, we will also be making those papers available to the group on that shared drive. With the idea that we might meet again in July, we would ask everyone to submit those papers by the next time we meet in July. In terms of a little bit longer term perspective, one of the goals of this task committee is to produce a report that would, again, as Walter mentioned, summarize sort of the state of the art in this area and talk about a future vision for collaboration in this area. And so that would be in the form of an ASCE EWRI committee report. And we would put that together at the conclusion of the webinar series. So probably sometime in about a year from now, we would be preparing and finalizing that type of a report. Again, there's a potential for having an in-person meeting in 2021. Another thought would be that we could have a special session at the EWRI Congress in 2021, which is probably going to be held in May or early June that year. So that would be another way for us to share the results of this webinar series with folks more broadly, and to share some potential outcomes of our meetings. So that's what we have in mind. Again, please give us your feedback. And if we do decide to go ahead and meet in July, we will be reaching out to those of you who had volunteered to speak at the initial workshop to see if you'd be available, and we would select a date for our meeting in July based on that. So that's our plan, and I'll pass it back to John then to see if we have any more comments or questions that have come in. And if after that, then we'll just wrap up and say thank you and goodbye.
Yeah, thanks, Regan. I think, again, the chat's working as it's supposed to. People are responding as they come in. So I think we're actually doing really well. And I think, if there was a question that was asked, please email me or Junseok, and we'll make sure that, we can answer it and send it out to the group. But yeah, I just want to thank everybody. I think, as a moderator, it was good. Everybody was on time, so that was great. But I learned a lot, so it was good. And I don't know, Junseok, do you have anything else you want to say before we wrap up?
John, real quick, this is Bill. I'd also like to solicit feedback on the format of this, the webinar through Teams and whatnot. If there were, I know there were some delays with me clicking through the slides. We sort of assumed that would be preferable to letting everyone control their own PowerPoint and maybe that going off the rails. But if Teams worked for everybody, if it didn't work, please send back any feedback. We have a couple of platform options, and we decided this was going to be the best and the easiest, but we might reevaluate based on if anybody had major problems with this. So thank you.
Thanks, Bill. Good point. I don't know, Junseok, do you have any final thoughts for the meeting?
Yeah, 1 point. So I know, thank you very much for everyone who participants, and also the speakers. Thank you very much. And also, if you're very much interested in joining the committee, we are very open. So please contact us, any of us, and then we would like to have a collective thought together, and then move forward with this very interesting effort. So I think the future is very bright for us, and then it's a very interesting area. So thank you very much, John, and then I'll get back to you again. So,
John, may I ask a question, a follow-up? This is Simone. I was wondering, Junseok or John or whomever knows, how would one become a member of this committee? Do we have to be WRI members? What is the process?
Simone, as far as I know, you don't. It doesn't need to be the member. I think this one, we can invite anyone. Regan, that's right?
Yeah, that's right. Maybe we can follow up with some information later about how to join the committee, but I don't think you have to be a member of EWRI. Although we would recommend it, but it's not required.
Okay, perfect. And then maybe just one suggestion, because we have this other parallel effort going on, and we've learned quite a bit since we first started. And one of my observations was, and I don't know if this helps with future planning perhaps, but what we noticed, and Alex can follow up on this too if he's on the call, is that it really helps to have regular conversations. Ours are bi-monthly, so every 2 months typically. But we find that it really helps keep our members engaged when we do that, and just keep kind of the conversation active and alive. And then the other thing that we've noticed is if we have actionable items and kind of put deadlines on ourselves, it also helps keep members engaged, and start with simple things that are more easy to do in a short amount of time, and then kind of make things more complicated, because a lot of these concepts that you mentioned here seems like it can get really complicated fairly quickly. So perhaps starting with kind of simpler things that could be done that motivate people and kind of make everyone feel good once those are accomplished. Perhaps that's a thought. But thank you all so much. And as I mentioned earlier, please just keep us posted on these efforts, and whatever we can do to help you and support you in those, we're more than happy to, as the AWWA Premise Plumbing Committee.
Thank you, Simone. Those are great suggestions. So let me just take a minute to thank the organizing committee. I think everyone saw the names on the first slide, but we had Steve Buckberger, John Burkhart, Walter Grayman, Tara Haxton, Robert Jenke, Junasuk Lee, and Bill Platten, who all put a lot of work into organizing this. So thank you so much to them. Thanks also to all the speakers today. You guys did a great job of introducing these complex topics to everybody and highlighting what the issues are and the research challenges, which is exactly what we were hoping for. So thank you so much. Thanks to Bill for running the slides and John for moderating, and for everybody else who was involved who I haven't mentioned. So thank you so much. And it looks like from the chat, folks are in agreement about planning this next webinar series to go into these topics in more detail. So the organizing committee will work on, what exactly that schedule and plan will look like, and we'll send out some more information to everybody on that. And we'll also follow up with a link to the shared drive where you can find all the materials from the meeting. So thank you very much to everyone. And we're even ending a little bit ahead of time. Let me just check with anyone from the organizing committee. Are there any other final comments?
We should include Simone and, the other AWWA committee person's emails in the whatever we send out afterwards, so that they can, if people are interested.
Sounds good. All right, well, we'll go ahead and wrap up then, and thank you so much, and please take care of yourselves and your families and your colleagues, and we hope everyone is doing well, and we will look forward to talking to you again really soon. Thanks so much.